the equation sheet? I sent it on an email this morning. It's on the website. Also on the website, let's see, where is it? Oh, it's on the, I sent y'all out a YouTube channel. Did y'all get that? The YouTube channel? Let me pull it up right quick. Oh shoot, I don't see it. Oh, there it is. Yeah, so on this, I have all the solutions for questions 1 through 12. So those are up there as well. Yeah, no multiple choice on the test, all 3 response. And there's questions 7, 9, and 12. 7, 8, 9, and 12 there at the end. All right, so as I told y'all, say it again, the test will be a lot like the homework. So that's how it's prepared for it, go through the homework. I'm going to recap everything right now. And the equation sheet should help you out a lot as well. I sort of changed a few things just to make it a little more palatable. But we're looking at sort of several big topics. Faraday's Law and Lenz's Law. Faraday's Law is when you have this changing magnetic flux, it induces an EMF. It induces an electric field, which induces an EMF. And those first 2 homework problems deal with that. It usually involves taking the derivative of the magnetic field function. So you give you some function that describes the magnetic field, and then you get the derivative of it, and then you also find the area in order to find the flux. And then you can find then the induced EMF from that. So that is here, where this is how I find my magnetic flux. Even though it's listed as a surface integral, usually those things do not change over space. So really, practically, this is just B times A. And for an induced EMF, this is then going to be equal to negative N. Right, N, remember, is just the number of turns. So if you have 10 turns of wire in a magnetic field, you just multiply it times 10. And so that's going to simplify in practice, as it does in your homework, to A times dB dt, where dB dt is just the derivative of that magnetic field, and then at a particular time. We had 2 or 3 homework problems like that, so you'll definitely see a problem like that, where you're applying Faraday's Law. Also wrapped up in that is using Lenz's Law. We did a couple different examples in class and in the homework as well. Remember, Lenz's Law you can use to determine the direction of that magnetic field, or the direction of the induced EMF. Lenz's Law is not listed here. There's not really an equation, but it just says that the induced magnetic field opposes the direction of the increasing flux. All right, or you can think about an increasing magnetic field. The flux and the magnetic field are very similar. So it's really in the direction of the increasing flux, but I'm going to cross this out and just say the increasing magnetic field. So for example, if I have a magnetic field that is increasing into the page, that means that my induced EMF is going to be out of the page. If this is a magnetic field that's into the page but decreasing, right, that means that the derivative is negative, then the induced EMF is going to be what direction? Excuse me, the induced magnetic field is going to be in the same direction, into the page. We did several examples like that in class. Now once you determine the direction of the magnetic field, then, as they do in the homework, you can find the direction of the current. And this goes back to our previous chapter. So for example, if I have a loop of wire that's generating this magnetic field, then I use my curl rule where, let's see, this is into the page, so that means this current will be going clockwise. Fingers in the direction of the magnetic field, your thumb is current. We usually did it the other way around, right? Thumb in the direction of the current, and the fingers wrap around to give us the magnetic field. So this current, for example, would be clockwise. A couple different problems where you had to do that in the homework, and we also did some in class as well. But you'll definitely see a problem like that, where I give you some changing magnetic field. It'll be some function, right? And you'll have to find the derivative of that, and then calculate both the magnitude and then of the current that is induced in this coil of wire, and then also by Lenz's law determine the direction of that current. You might also have, like we did in the homework, we have an extra battery, and then determine what is the net EMF. You know what I'm talking about? So for example, if I have, let's say that this EMF is 10 volts. That's what you found when you calculated it up here. And I have a battery that is like this, that's 5 volts. That would mean the net EMF would be 10 minus 5, because this battery is going to cause a current to go in that direction, in the opposite direction. So my net EMF would be the difference of those two numbers, 10 minus 5. It would always be positive, my net EMF. We don't really have a negative direction for EMF. Okay? Definitely a problem like that. One or two problems like that. Probably just one. Alright? Y'all could do that? Y'all could do that right now, right? Maybe? Probably? Alright. I'm going to clear all this. And then after that, we have a series of circuits. We have LR circuits, LC circuits, damp RLC circuits, and then our three very simple circuits. That is an EMF source, an AC EMF source with a resistor, a capacitor, and an inductor. I've sort of rewritten some of these. They're still the same as what we did in class, but I've rewritten just a little bit, and I'll tell you about that in just a second. And then finally, the RLC circuit with the forced oscillator. That means an RLC circuit that has a generator in it. Right? You'll likely see probably one of each of these. So, there are similar examples in the homework, and then we work through some problems in class. I'll also likely ask you to describe what the functions look like for various things. It shouldn't be that hard if you're familiar with them, because the functions are described here in the equations. You just need to recognize what they look like. I'll draw them as we go through. So an LR circuit, remember, looks like this, where I have a generator, I have an inductor, and then I have a resistor. And remember, the basic idea in this is that as my current is increasing, that this inductor generates an EMF. It generates an EMF by this function. Okay. As the current increases, it generates an EMF. I might ask you to describe this in words as well. But as the current increases, it generates an EMF in this inductor, and so that slows down the current. So the current doesn't reach its maximum value for a while. And so if I were to plot then the current versus time, it looks like this. All right, it doesn't reach max current immediately because the inductor impedes the current. It generates an EMF that opposes the direction of the generator, opposes the direction of that power supply. All right, the function that describes this current is here. This is the EMF of our generator, this is the resistor, and then I have this function. Right, and it follows this path. It takes about 10 tau. This is just like we had for capacitors. This is my time constant, my inductive time constant. This is different from the time constant we had before with RC circuits, but it's the same function and same idea. So after 10 tau, just as we had with RC circuits, this the circuit reaches equilibrium. You had a problem, a homework problem that was addressed that. I could also ask you, I likely will ask you, just what is the current at any particular time? But that should be pretty straightforward. It's just plugging in for this current equation right here. Okay? So you probably will have an LR circuit like that. I'll probably ask you to draw the I versus T graph. All right, I'll tell you that it's an LR circuit, but you'll recognize it too because it'll have these three components. L is your inductor, R is your resistor. This also will have an EMF generator, a power supply. And I might ask you in words sort of what happens here, why the current doesn't go up right away, and then also you have to calculate the current at a particular time. You have to do that right now? Okay. I'm going to erase all this. Now let's look at LC circuits. LC circuits are just capacitors, and looking at LC circuits, I just have a fully charged capacitor and an inductor like this. So I have a capacitor and an inductor, and you'll likely have a question describing just what happens here to the energy. The energy of the inductor, UB, is equal to 1/2 Li squared, and the energy of the capacitor, UE, is 1/2 Q squared over C, or CV squared. Those equations are given up top, in the top part of that equation sheet. Remember what happens here is these are completely conservative forces at play. The electric field and magnetic field are conservative. There are no resistive elements. That means that this is going to go on forever. It will never lose energy. Obviously, it doesn't go on forever because the wires have resistance. But in theory, it could go on forever, transferring energy back and forth between the electric field and the magnetic field. I might ask you some questions about that, just sort of how that happens and what happens. So if I were to plot out the energy, that would be UB, for example, and this is when this is 0, this will be at its max. You know, like that. So they're going to switch that energy back and forth, where this is my energy in the magnetic field, and this is my energy in the electric field. Some questions I could ask you about this. I could just ask you to find what is the current at any particular time in this LC circuit. You would have to be able to know how to find I max. You know how you define the maximum current? Remember how we did this? Set the energies equal, right? So I know that these energies at their maximum are going to be equal, and so when UB is at its maximum, the magnetic field energy, I just say 1/2 Li squared equals 1/2 Q squared over C. Then you would have Q, or I would, as you had in the homework, I would tell you that the capacitor was charged by a battery prior to being hooked up to the inductor. So to find the maximum current, you do that, and then times the sine of omega t. That describes the sine function right here, the sine of omega t, which is the red. Omega, which is our angular frequency, is 1 over root LC. Omega comes up a lot in these circuits because they're oscillatory, so make sure that you understand what that means. It is, I give you the equations describing omega. Can I erase everything here, y'all? Hey, Courtney. All right, so omega is our 2 pi f. This is our phase, or excuse me, our angular frequency. It's related to our regular frequency by 2 pi f. It's also related to our period. We use this during the chapter, but I want to include it here. It's 2 pi over omega. That's our period. So that describes the period of those oscillatory functions, those trig functions. All right, you with me so far? Are you afraid of this step? I don't want you to do that. I don't need you to do that. But we'll take some preparation. Make sure you're up on that homework. Okay? Let's see, a couple more things. Oh, so the damped RLC circuit. You'll likely have to draw the figure for this as well. So remember the damped RLC circuit, it takes the LC circuit and the the LR circuit and it puts them together. So our function then, for the LR circuit, it had an exponential function, right, that looked like this. For the LC circuit, it had this, the current was a sine function. For the damped RL circuit, it's going to look like this. It's going to be a sine function that's damped. That means it decreases with time. It decreases by this exponential function, e to the minus RT over 2L. And then this goes as a cosine omega t plus b, which is the phase shift. Let's see, cosine of 0 is 1, right? Yeah, so actually, the axis would be right here. All right, where this would be the charge on the capacitor versus time. Remember, this RLC circuit is a resistor, an inductor, and a capacitor, and nothing else. It doesn't have a battery. It's not until we get to the forced RLC circuit, the forced oscillator, that we get this. All right, so none of these have power supplies. The LR circuit, the LC circuit, or the RLC circuit. None of those have power supplies. Okay. Again, let's see, what did I have you do in the homework for this? I think I just had you you had to find the charge at particular times. In the homework, I'm not going to belabor the homework too much unless you have particular questions about them, but in the homework you have to find the charges at different period intervals. So remember, on a cosine function like this is 1 period, and so you had to find the charge on the capacitor at different period intervals. And in that, when you see the homework, you'll see that we just leave out the cosine function because that cosine function is just equal to 1 at these peaks. So you don't need to include the cosine function. You just consider that exponential function. Okay? So that's an RLC circuit. And then we have 3 different circuits. The purpose of those is really just to introduce phasors and to lead up to the LRC circuit, which was forced. Can I clear everything here? You have questions? Particular questions? Okay. Let me clear this. Let's look at these 3 circuits. I've rewritten this just a little bit because I've written them all so that they're sine functions. But if you look back in your notes, you'll see that in the capacitor circuit, that this function was a cosine. The reason I wrote it as a sine is before we had it as cosine with no phase shift, but I included a phase shift. So I just did that to be symmetrical. So this is a sine function with a phase shift of 0. This is a cosine function with a phase shift of 90. And then this is a sine function with a phase shift of minus 90. If you notice in your notes, this is a minus cosine function. But a sine function with a phase shift of minus 90 is the same. I just made it to be symmetrical. Let's see. Could I ask you probably have one question about one of these. The reactance is pretty important here. Remember, we can describe our voltage based on our reactance, our capacitive or our inductive reactance. On the homework, you had a couple problems, and you'll have something similar to those where I asked you what is the current, and in the current on all of these, the maximum current is equal to I equals V over XC. This is like Ohm's law, right, where XC is sort of replacing a resistance. Capacitors don't really have a resistance, but they do impede the flow of electricity based on the frequency and the capacitance, that XC, and so we just treat it just like Ohm's law. I could just ask you a time, just give you a time, and ask you for the current at a particular time, but that would be pretty simple, just put in the right numbers. Make sure that you're up on that, if you can do that with your calculator. And of course, I'm going to change this on the equation sheet, but this should not be 90 degrees, it should be pi over 2. I'll change it for what I give you on the test. everything should be in radians when we're dealing with this, no angles or degrees. So I'll fix that. All right. Look at the homework questions on this. They'll help you. Again, the test will closely follow the homework. It won't be exactly the same, but of course the numbers will be different, but the questions will be largely the same. You can do the homework. You can do it. All right. So that's what I would focus on. Also, be able to draw these various plots. And in the solutions for the homework, I draw them and stuff as well. All right. Yep. If I smile, I think it's going to be okay. Okay, yeah. Josh is not going to do well, but everybody else is going to do well. Okay. Okay. RLC circuits are the last thing. RLC force circuits. So this is where I have a resistor, an inductor, and a capacitor, and they're operating at this at a certain omega d. Omega d is the angular frequency of our force of our AC generator. Really, just sort of dealing with phasors here. Remember, with our phasors, that these I talk about this in the screencast. That if I draw the phasors for these, I have a phasor that is the current in the circuit. So that would be like I, R. And then I have phasors for each of the voltages. So I have VR, which is in this direction. And then the other two, VL and VC, either lag ahead of, or lead the voltage across the resistor, or the current in the circuit. And we had that Eli the Iceman, that mnemonic, if that helps you. Also, if you or never mind. Yeah. So anyway, those are our phasors. Be able to draw the phasors, and as you do on the homework, also if I give you a sine function, be able to draw the phasors for different points. I think y'all are okay with that, but you'll certainly see a problem. Just sort of general phasor thing. We're not going to get too much in the vector quantity. But remember, when we found the net EMF of these, we found that we're finding this impedance, and that's where this comes from. It's just the diagram here. So, given one of these, I could ask you to find the impedance and to find the current at any particular time. I think that's it. There were several questions on this, but they were all pretty straightforward. This is number 12 for your RLC circuit, and you'll likely have one of these. Almost certainly you'll have one of these. So basically everything. There are some repeats of questions on these, so I might consolidate some of those for test questions. But largely, your homework will be a good guide for what to expect for the test. I try to condense everything, because I know I've sort of thrown a lot at you in the past couple of weeks. Right? Have I thrown a lot at you? It's sort of different stuff that we've been doing. Then there's this idea of resonant frequency here. The resonant frequency, if your circuit, remember, has a certain natural frequency, based on the interchange of the energy between these two devices, right? That going back to that LC circuit. So they have this natural frequency, but your circuit will go at the frequency of your generator, because your generator has a certain frequency too. And whatever your frequency of your generator is, that's how your current in your circuit will respond. But if you've matched your frequency to the natural frequency of these two devices, their natural frequency and how they exchange energy back and forth, then you get a maximum current. You get a current that's a lot bigger. I addressed that in the homework, so if you're likely to see something like that as well. The final thing was pretty simple. I think it was pretty simple, was the transformers. That's pretty straightforward. More turns, more voltage, and it goes as a linear relationship. So that's here. There's a homework problem. You'll see something like that as well. I'll ask you, is it a step up, is it a step down transformer, or what is the output voltage? It won't be the same transformer, of course. You'll see a different transformer in different transformer. But you'll need to know, is it step up or step down, and then what is my output voltage? That's the whole test. Okay, that seems okay to you. That seem okay? No multiple choice on the test. That's it. As I said, that's good for y'all. It's
students tend to be more poorly than multiple choice. Should be the last year, I think, previous one. All right. So that's your deal, right? Y'all like the previous one, right? Yeah. We'll try it out next year. I was like 40 students. In this class, 14. I mean, it used to be just chemistry majors in the class, so there would be like 2 or 3 a semester. But we like the geometric students. And who else is geometric? Daniel. I like it. Y'all are good students, so work hard. Yeah, before you got here, it's like, ah. I agree. All right, guys.
The number of turns, I guess it's mistake. Like that just means the number of loops.
Right.
Okay.
Like we're talking about it on. It comes up several times, right? It comes up with Faraday's Law, and it also comes up with this. Now with the transformers, you have an iron core. It's a laminated iron core, so no current flows through it. And then you have these copper wires that come around. And so, for example, this would be 1, 2, 3, 4, or no, 3 coils, 3 turns. I'll tell you, you won't have to count them on the picture, but that would be 3 turns. And then on the other side, for example, I would have a different number of turns. All right, so that has 6 turns. Would this be a step up or step down? Like if this is my input and this is my output, is that a step up or step down transformer? What is it? It's a step up, right? Remember, each coil of wire has the same E and F. So like if each coil has 2 volts, this would have 6 volts, and this would have 12 volts. That comes out with this. Yeah, but any other questions? No? Homework. You want to really focus on the homework. Go back through the notes a little bit and just sort of familiarize yourself with the different circuits. Because I might ask you some in words to describe what happens here. What happens to the interview, the LC circuit? What happens, to the LRC circuit when you have this damping effect? And I'll ask you to draw those, sketch out those plots, those sort of things. You've done those things before. That's not like it. All right. Play the G to help you. If you feel like there's anything missing from that, I'm pretty sure there's not. But if you want something that is something that, how about the answers? 1 through 4. Right? Yeah, that's a good idea. Okay. Anything else, Joe? I don't know. It's a fancy jacket, so you can open it up.
They just caught my eye, and I thought it was very weird.
Yeah, it's the.
It's like, oh, it's getting a little hot. Yeah, it's like a lot of elderly things.
All right, folks. Y'all have a great weekend, okay? Don't study all weekend. I think it's one of the nights, so you don't
Yeah. I get outside.
The weather would be nice. Have a nice day.